What if your LLM app looks perfectly healthy, returning 200 OK all day, while quietly getting worse? In this lesson, we'll examine silent model drift, quality failures that hide behind uptime, latency, and clean infrastructure dashboards. So far, we've diagnosed the more obvious production failures: fragile architecture, runaway token costs, reliability breakdowns, and self-hosting instability. Now we turn to a quieter risk. Your dashboards may look green, even as answer quality drifts and user trust starts to erode. In traditional backend systems, success is often easy to read. The service is up, fast, and not throwing errors. With LLMs, that is only part of the story. A 200 OK means an answer came back. It does not mean the answer was accurate, grounded, safe, or useful. A model can respond quickly and confidently while giving the wrong advice. So reliability has two layers: system reliability, which keeps the pipeline running, and semantic reliability, which checks whether the answer actually serves the user's need. That second layer requires evaluation and feedback. A silent quality regression is like a plane drifting off course, while every engine gauge still reads green. The system is up, latency is fine, no exceptions are firing, but the answers are slowly getting worse. Maybe the model hallucinates more often, uses stale facts, gives irrelevant summaries, or shifts tone unpredictably. Users usually feel that decline before monitoring catches it. Later, it appears as support tickets, lost trust, lower conversion, or churn. The core issue is tolerance. If you never define the expected path with baselines and evaluations, you cannot tell when the product has meaningfully drifted off course. Quality regression is not one generic failure. LMs can fail in several distinct ways, and each one needs different detection. Incorrect answers are factual failures. The model invents, misreads, or cannot support a claim. Stale answers rely on outdated training data or old retrieved documents. Unsafe answers cross policy, privacy, compliance, or brand boundaries. Low-value answers are more subtle. They may be true, but still vague, incomplete, or not actionable. Strong evaluation separates these categories, so teams can measure the right risk and fix the right cause. The prompt is part of your application's control plane, not just text. A small change from concise facts to detailed answers can shift verbosity and tone. Changing "use the tool as needed" to "avoid using the tool" can alter retrieval, refusal patterns, and factual grounding. That is prompt drift, behavior changes caused by edits that may look harmless in review. Treat prompts like code. Version them. Test them against representative cases, and tie deployments to prompt revisions. Otherwise, regressions become much harder to explain after users see different behavior. Retrieval drift happens when the model stays the same, but the knowledge pipeline feeding it changes. New documents can introduce duplicates, stale policy, or conflicting facts. A new embedding model can move similar items into different neighborhoods, changing the nearest results. Filters and ranking rules can also hide the best source and promote weaker ones. Since the LLM answers from whatever context it receives, generation metrics alone may miss the root cause. For RAG systems, evaluate retrieval directly: coverage, freshness, relevance, and whether gold sources are actually retrieved. Chunking drift is easy to miss because nothing appears broken. The retrieval system still returns passages, but the model may see the wrong slice of meaning. If chunks are too small, definitions, exceptions, or dependencies get separated. If they are too large, the answer is buried in noise, and token cost rises. Parsing errors are just as damaging, especially with tables, headings, footnotes, and legal clauses. Treat chunking as a versioned retrieval choice and test changes against known questions and the exact source passages you expect. User behavior drift appears when the people using your application no longer match the people you tested with. Early evaluations may cover support questions from internal users, but growth brings new customer segments, new vocabulary, different languages, complex files, and messier requests. What used to be a rare edge case can quickly become normal traffic. That matters because prompts, retrieval rules, and evaluation sets may all be tuned to yesterday's audience. Production monitoring should track input patterns, not just model errors, and tests should be refreshed as the user base changes. Input distribution shift focuses on the shape and difficulty of the requests reaching your system. Users may send much longer prompts, changing latency, cost, and context assumptions. They may move into new domains where the model or retrieval corpus has weak coverage. They may upload messy formats like PDFs, tables, screenshots, or OCR text, which can break parsing and grounding. Some inputs are intentionally hostile, using prompt injection or adversarial wording. Treat these as monitoring dimensions, not edge cases, because shifts often arrive gradually. When you depend on a hosted LLM, your application is not the only thing that can change. The provider may upgrade a model, patch safety behavior, reroute traffic, or retire an older version. If you call a floating alias like latest, the same request can start producing different answers even though your code did not move. That makes incidents harder to reproduce, debug, and roll back. Production systems should treat model selection like any other dependency. Pin explicit versions, monitor output quality, and run regression tests before accepting upstream changes. Traditional monitoring tells you whether the machine is healthy: latency, errors, GPU memory, and token usage. But a healthy machine can still produce a bad answer. It might be ungrounded, unsafe, outdated, or simply unhelpful. That drift often shows up later through churn, weak engagement, or support tickets. LLM observability adds the missing context: prompts, retrieved documents, outputs, user feedback, and evaluation scores. The goal is to connect operational health with answer quality, so teams can catch degradation before users lose trust. Quality baselines turn evaluation from opinion into engineering practice. Start with a golden test set: real or representative user queries, the source documents that should support them, and examples of known failures. Then label the expected behavior, including answer traits, citation requirements, refusals, and policy constraints. Before changing prompts, retrieval, models, or data pipelines, run the same tests again. Compare results against the baseline using metrics like groundedness, relevance, citation accuracy, refusal accuracy, and task success. The goal is not only pass or fail. Track trends so silent degradation is caught early. Once drift is detected, resist the urge to roll everything back immediately. Treat it like an incident. Compare recent changes in prompts, corpus, embeddings, chunking, and model versions. Then segment the failures to find the boundary. Which users, query types, languages, formats, or tenants are affected? Reproduce the issue, isolate the component, and contain exposure with canaries, shadow evaluations, and staged rollouts. Finally, keep clean rollback paths for prompts, indexes, models, and retrieval settings. The objective is controlled mitigation, not panic. Reduce impact, validate recovery, and document what changed. Silent drift reinforces the core lesson of this module. Production health is not just uptime. Quality can degrade through changing prompts, data, users, retrieval, or models. Reliable LLM systems need observability, baselines, versioning, tests, canaries, and rollback. Next, we move from diagnosing fragile GenAI systems to designing controlled, cost-optimized serving architectures.